Again, welcome everybody back for the last session, this afternoon session. I just want to do a commercial here one more time. Remember to write your notes down and pass them on in. Caitlin's going to collect everything too. We'd like to know what you think we need to do to make this whole thing a success. Would also like for your thoughts on what would be a good topic for the next joint meeting between Geothermal and SPE, which will probably be in a couple of years or a year and a half. We'll want to do another one. It's been suggested that we may do casing design or casing failures, which would incorporate some corrosion as well as some cementing remedial work. So kind of keep that in mind and pass in some small note. All you got to do is a couple of subjects and pass everything to Caitlin, and Caitlin, you'll summarize everything, get it back to us, right?
Yep.
All right, with that, we'll start the second session. Got our chair, Bob's over here, and Caitlin's going to take it. Y'all are all geared up, ready to go. So, welcome.
You. So our session 6 is actually called Problems and Solution. And one of the reason we do that, is because for every problem, it should be at least one solution. And for any solution, we're going to have more problems. So therefore, Bob and myself, we prepare several presentations here that may either help you to solve the problems or will bring more problems to the solution we already had. And our first speaker today, Jared Wise, we'll talk about, as you can see here on the slide, the reservoir depletion needs to be included in the top of cement selection. Again, we talk about, well integrity and the very important aspects and relationship between cement, casing, and, planning wells. Jared, whenever you are ready, you can start.
All right, thank you for the introduction. So like Caitlin said, my name is Jarrett Wise. I was previously a PhD candidate at University of Oklahoma, and now I recently just defended and graduated, so now I am a postdoc for the USDA. Like mentioned, the title of this talk is Reservoir Depletion Needs to be Included in Top of Cement Selection to Prevent Leakage. So what exactly does this mean? So we all know that when a well is completed, the cement used to hold the casing in place is usually only a partial length of the casing to, at least in oil and gas wells, to save on cement costs. So this work investigates the leakage pathway between the cement sheath and the casing from the simulation depth to the top of cement depth, and if the length of the cement is critical in preventing leakage or not. From this work, we determined that the length of the cement can be critical in preventing leakage depending on the leaking fluid. All right. So before we get started, we'd like to thank the National Academy of Sciences, Engineering, and Medicine Gulf Research Program for funding this project. Without their support, this work wouldn't be possible. So the title of this talk is looking at wellbore leakage. The majority of the research I did during my PhD, and we're starting to transition to geothermal a little bit, but we focus mostly on oil and gas wells, specifically in the Gulf of Mexico. So we'll just do a quick little bit of background. So in the Gulf, there's over 50,000 oil and gas wells, in which 30,000 are plugged and abandoned. And as we can see from this graph, the number of wells that are being plugged and abandoned, either permanently or temporarily, is increasing each decade. With an increasing number of wells being abandoned, we need to ensure that they're providing zonal isolation and not leaking. So how do we determine if a well is leaking? Measuring these wells directly would be expensive since they are offshore and current regulations don't require monitoring after they are abandoned. And it would be difficult to actually measure any leakage since they're underwater in extreme conditions. So numerical models have been developed to predict which failure mechanisms are likely and how they show the cement sheath debonding as the primary failure mechanism. So leakage pathway models force hydraulic fracture propagation, but they're unrealistic for wellbore leakage scenarios because we're not actually fracking the well, it's more of a natural process. So And then finally, different leakage calculators exist in the literature, but the main limitations with them are they either assume arbitrary microannuli or they model water as a leaking fluid. So, right. So this work was originally submitted in the fall of 2019. Since then, the pandemic has changed a lot of things and the date of this conference a few times. So we've had some work published in between that's related to this presentation. So kind of just do a little overview of the work that we had initially thought of that went into this. So first, the paper that started us down this path was our ARMA paper in 2019, which we determined that cement sheath debonding is the main failure mechanism in these wells. Then we expanded our research to quantify the microannuli due to pressure depletion or temperature cycles. And then our last ARMA paper quantified the fracture volume from the simulation depth to the top of cement depth. So this, so what I'm talking about today is going to be kind of a brief overview of these three papers and how they build onto each other and how we can use these for oil and gas wells or geothermal wells. So since this work is based in the Gulf of Mexico, a case study well located in the High Island OPD was selected. For this region, there's over 3,800 wells ranging with depths from 93 meters to over 8,000 meters deep, with the majority of them in the 2,400 meter range. The case study well was chosen with a similar depth and well logs were purchased for this well. And the figure on the right shows the casing string design, pore pressure of the different depths, and the drilling fluid weight from the well log. For the case study well, we focused only on the intermediate casing string. So based from the well logs, the top of the cement for the intermediate casing string is located at around 792 meters. But based on regulations in the Gulf of Mexico, the minimum length of cement is 500 feet or 152 meters from the bottom of the casing, which make the top of cement at this location. So now we'll look at how these two depths can affect potential leakage in the case study well, from using where the operator chose their top of cement to just doing the bare minimum required in the Gulf. So the overview of this work is a numerical model. So the numerical model we used was a finite element analysis, and a snapshot is shown on this slide. The picture on the left represents a 2D snapshot of the model, while the pic on the right shows the 3D geometry. The model was created and simulated using finite element software ANSYS, along with some custom code to incorporate pore pressure. The model itself is composed of 3D quadratic thermoporoelastic elements that include the traction separation law to replicate cement sheath debonding, so we can quantify the microannuli. The element dimensions are designed so they're kind of smaller in the areas of interest, such as the casing, cement, and near wellbore region, and then larger towards the boundaries just to save some computational time. So, and the mesh was verified and the methodology was verified using the analytical solution of the Kirsch analytical solution. So since this model stage, these are some of the stage steps we used within it. So the stage steps start from simulating the geologic conditions with the in-situ stresses and pore pressure. Then the second step consists of the hole being drilled with a fluid weight applied to the rock formation. The casing is added to the hole within the third step with the fluid weight applied to the inner and outer surfaces of the casing and rock formation. And then the wellbore is completed in the fourth step, which consists of two parts. So since the completion of the well consists of putting cement between the rock formation and the casing, we replicated the liquid part of the cement slurry is being pumped into the wellbore between in all the void spaces, so between the rock formation, the casing, and on the inside of the casing. And then we replicated the hydration process by removing the liquid elements into solid elements, incorporating a framework stress and pore pressure. And then the well is producing, in which the mud weight is removed and production pressure is applied in the well. And this is the step that we saw in the first two papers, is where we're really getting the microannuli formation. Is when you go from a mud weight to a production pressure over time, which is depletion. you see, excuse me, you see that due to the different stiffness between the casing and the cement, you start to get microannuli formation between the cement and casing. So then the next step is, how do we model a fracture propagation? Because as you saw from the previous slide, the model is a 3D model, but it's a thin slice. So how do we model from about 3,000 feet or 3,000 meters? So to do that, we had to get kind of creative with our modeling approach. Since a 3,000 meter long wellbore cannot be modeled with the degree of accuracy needed due to just memory constraints in computers, supercomputers, all the computers, we had to segment the wellbore into thin sections and created basically a for loop that modeled each section individually and took the pressures and stresses from the previous one and propagated them up. This way, we were able to assume that the geologic stresses are constant within each individual model while being able to include the gradient of them as the well got shallower. We used this static single-phase gas equation shown on the screen to model the gas pressure within the microannuli to represent our fracture pressure. So this equation relates the inlet and outlet pressure with a specific gravity of the gas, the length of the segment, which was 1 meter in these simulations, I believe, the compressibility of the gas, and the temperature. For this model, temperature was assumed to remain constant, and the compressibility of the gas was calculated using the empirical formula from Shell for methane. So from the following figures are the loads and stresses within the model from the simulation depth to the top of the cement depth. The internal casing pressure and microannuli pressure are determined from the static single-phase gas equation. The pore pressure, drilling fluid weight, cement stress, and minimum horizontal stress are all determined from the well drilling reports. And then the overburden stress is calculated from the Gulf of Mexico correlation. And the maximum horizontal stress is just the average of the overburden and the minimum horizontal stress. So now that we have a model, we'll look at some of the results we have. So to get started, from the journal paper I mentioned earlier, we kept reducing the production pressure to represent a depletion in the wellbore to see at what depletion percent do we need to get to before we start getting a microannuli between our cement and casing. So the figure here shows the microannuli formation at the casing cement interface due to a reduction of pressure, so depletion. And then we also did temperature for the paper, but today we'll just focus on the pressure. So we see that the microannuli actually starts to form around approximately a 45% reduction in pressure from the mud weight. And we can see that it goes all the way down from like nanometer size all the way to roughly 80 microns. So then once we got the microannuli due to pressure, we decided to do a sensitivity analysis to see what's the parameters in the wellbore are really predominant in causing microannuli to form. So first we chose a 29% reduction in pressure, which, as from the previous slide, you saw we didn't have any microannuli yet. So this should result in 0. But we see that just changing the cement Young's modulus, the setting stress in the cement, the hole size, and the casing thickness, we can actually start to get microannuli to form, whereas it was none of it forming at this pressure. So if we continue to reduce the pressure up to 44%, we see that our microannuli are starting to get bigger in magnitude with the same parameters as before, but now we're starting to add in a few more, like the Young's modulus of the rock and the tensile bond strength. But we really see that the hole size and casing thickness are the main ones, where they take it from like 1 micron all the way up to about 40 to 50 microns in size. So pretty significant change. So same thing with reducing the pressure down to 50%. We see that the base case has a microannuli size about 10 microns, but now the parameters are starting to change it more, where if you have a smaller hole size, you can actually reduce the microannuli size. But if you have a bigger hole size, you're getting up to almost 80 microns. Finally, if we reduce the pressure down to 67%, which is, I believe, hydrostatic pressure for this well. So basically the well is completely depleted and just has a water column in the well. You can see that the base case has a 30 micron microannuli size, but if you have a huge hole size, you can get up to about 130 microns, or if you have a thin casing, you can get up to almost 100 microns. So looking at the trends from this sensitivity analysis, we see that hole size and casing thickness are the two main parameters that have the largest effect on microannuli size when you change the pressure. So the interesting thing is with this, I know, especially in the cement community, everyone wants to look at additives in cement to basically hold up integrity. But from this analysis, we see that really the additives in cement, so like the Young's modulus and Poisson's ratio, aren't having as dramatic of an effect. Like the rocks, the elasticity of the rock is a little bit more than the elasticity of the cement, and you can't change the rock you're drilling in. Same with the hole size and casing. You can't really adjust those very much just due to the cost of it and the safety factors involved with drilling the hole. So that was one interesting thing we came up with. So then, like I said before, we investigated the effect of pressure and temperature and saw that for a well, you can have very many different scenarios. So if you have a reduction in pressure, but like an increase in temperature, they kind of counter affect each other, as shown by this heat map on the screen. So you see if you have a 60% reduction in pressure and a 60% reduction in temperature, you're going to get the biggest microannuli size. So how this affects geothermal, because geothermal, you're dealing with temperature cycles. So that might be something we have to investigate more, trying to prevent leakage from geothermal. And with the temperature cycles, we're probably going to have pressure cycles too. So those two can compound on each other, or they could cancel each other out. It just depends on the specific scenarios and the loading patterns. So anyway, that's not the point of this talk. So the point of this talk is, how does the top of cement affect the leakage path? So using the method described a few slides ago, we can determine how the microannuli propagates up the wellbore with the gas fracture pressure as shown by the orange line on the screen. And for comparison, we used basically water in the fracture. So just the pore pressure of the water with water density and all the good stuff with water. And that's shown by the blue line on the screen. So as you can see, the fracture, so we initially get a microannuli at the bottom of our intermediate casing string of about 23 microns. So if we have gas inside our fracture, it actually goes up the cement sheath and propagates and causes the microannuli to increase in size as we get shallower and shallower. So you can see the top of cement is about 762 meters. So with gas in our fracture, we're actually getting a complete leakage pathway. But with water, water starts out at the same 23 microns, but actually goes smaller and smaller until it closes up about 1,524 meters, just due to the gravity of water taking away some of the propagation pressure. So we see that both, so with the top of cement that the operators chose for this well, like if we have gas in our fracture, we're going to have leakage. But if we have a water-induced fracture, we're not going to have any leakage. But looking at the requirements for the Gulf of Mexico, if you just do the bare minimum cementing requirements, so the 500 feet of cement, you see by the red line, we actually have a complete fracture path for both water and gas. So if the operators are cheaping out on cement, in this case, they would have leakage in their intermediate casing string, no matter what the fluid is, well, assuming water or gas. So in conclusion, the staged 3D model was used in conjunction with the traction separation law and was performed to replicate fracture propagation to the top of cement depth. And the case study well in the High Island OPD in the Gulf of Mexico was analyzed to determine if a continuous leakage pathway was present depending on the length of the annular cement. So the main conclusions are that changes in casing pressure, so like depletion and or temperature, can cause microannuli to form at the bottom of the casing string. The most sensitive parameters affecting the microannuli are ones that you are kind of stuck with. So like the size of the hole and the thickness of the casing. So then the 3D model was performed in segments to replicate fracture propagation to the top of different cement depths, and the length of the cement sheath can determine if the well is leaking. So in this scenario, the minimum length of cement results in both water and gas leakage, whereas the original length of cement only resulted in gas leakage. So thank you for listening to this talk, and please feel free to reach out if you have any questions.
Thank you, Jared. Thank you very much. Very interesting presentation. So we have a few minutes for questions. If anyone from audience have questions, I've seen that there's some question on the Zoom. I will try to read them too, but let's see if we have any question from you.
If I could, I'd like to ask a question. This is Daniel Boer. Thank you for the presentation. Interesting. I was going to ask if you'd considered the hydration volume reduction in your model as a cement will shrink, and also the pore pressure of the interstitial water as the cement hydrates, because in other modeling I've been involved in, that will probably, I would expect it to make results even worse. So.
Right, yeah. So to answer your first question, we did not assume any shrinkage in these models, just to keep them as simple as possible, because what we theorized with shrinkage is you're going to get even more of the microannuli. But just since our models weren't as complicated as some of the others, we weren't able to replicate the hydration process within the cement. That being said, we kind of cheated on using the pore pressure from the formation. So we did include the pore pressure in the cement and in the rock formation. So we saw that definitely made a huge difference in this.
Thank you. Question regarding your 3D finite element analysis. I mean, I've seen a lot of modeling in 2D. Mm-hmm. So adding an additional degree of freedom, I mean, what kind of calculation power do you have? Is it a supercomputer submerged in liquid nitrogen, or how do you get to calculate in a timely fashion the simulations by adding that extra degree of freedom?
So that's a good question. So really with these ones, they didn't take very long to replicate. So since we did a thin section, we only had about, I think, 2 or 3 elements deep in the third dimension. So it came out to, I think, it was either 18,000 or 24,000 elements with these models, but they took roughly about between 5 to 10 minutes of simulation. And then to do the entire length of the cement, it took, I don't know, probably about 4 or 5 hours. But we just used a regular desktop computer with 64 gigabytes of RAM. But we spent a lot of time modifying and tweaking the simulations to make sure they're accurate, but also to reduce the number of elements, because that would lead to a lot of headaches and time consuming.
So it looks like we have a comment online. I would like to read it. I don't know if everybody can read it, but it's a very interesting one. Around 1990s, plug wells in the North Sea were observed with side scan sonar, and 100% were found to be leaking, as evidenced by gas bubbles coming up from the location. Some similar work was done subsequently in the Gulf of Mexico, same results. A joint API industry group studied the issue and came to the same consensus. The cement sheet had failed without focusing on the mode of failure. So this is a comment we got from Oliver Coker, which was online.
Yeah, that's very interesting. I like to look at those studies to see them, but that is interesting and makes sense from what we've kind of seen.
So 1 more minute, one last question in case you guys have.
I have a quick question, and that is, where would I find the results of this work?
Yes.
And then secondly is, I know it can be, but we would like to see the results of the thermal side as well, and hopefully extend it to geothermal wells in the future.
Yeah, that's very good. Thank you. So the slide on the screen right now, you should be able to see. So the thermal stuff was included in the journal paper, the 2020 journal paper. And then pretty much the first one is just doing a basic sensitivity analysis. Then our journal paper included the thermal stuff. And then our last paper went from the bottom to the top of the cement. And then we have a paper in review right now that's looking at the different leakage rates.
Okay, great. Any other quick questions here? Okay, well, thank you very much. Great work.
Thank you.
Thank you, Jared.
Okay, our next paper is Kathleen himself, and that's shear bond strength, oil well cement, and carbonic acid environment, and the effects of pressure and temperature.
Thank you, Bob. I'm just trying to get this. That's so I'm not sure if you guys are already tired of hearing about shear bonding and tensile bonding strength, but unfortunately, this is another paper. So the good news is that this paper shows that actually you can get better bonding in some cases, and that's why I believe it will be a very interesting paper to look at. And as you can see here, my co-authors, Ramadan Ahmed, is the one that ran the research project and did a lot of planning of the experiment. And of course, the students, John Huang and Saga Tail, that helping with doing a lot of testing, as you're going to see here. And then Sabnash Hash Shah was the co-authoring here by being, providing very amazing input for the testing. What we have done in this test was actually to look at the same shear bonding, but from a total different approach. And this approach was what happened if we have CO2. And particularly here, we were using a dedicated cement recipe, which was designed to have about 35% of silica flour. And that's why we believe that this presentation is very nice, linked to geothermal as well. And, on these samples, we've done, bonding. We've done some other tests that I will present, which were used more or less as a reference correlation between our shear bonding, to this. What you're going to see here will be samples which have been done by being aged for 14 days in autoclave. And, they were tested after being extracted from autoclave. And we are using different aging pressures. There were two ranges, 21 and 62 megapascal. If you will always have question about why the numbers are not round, is because we convert everything from PSI to megapascal in here. And we use 10 to 100% CO2, as a solution in the water. And I will show you how the autoclave looks like. Now, degradation is a big issue, and we know, for a long time that, cement degradation, happens in the presence of CO2, although there are a lot of discussion right now, what is the right model for degradation. But the important here is that in the cement, we have the carbonation of Portlandite and the carbonation of CCS phase. These two are very important for the degradation process that I will show you in what comes. For that, we've been using cement class H. We added 35% by weight of cement of silica flours, and then a lot of other chemicals, which we are trying here to replicate a given recipe that was proposed to be tested. And that's why we have the anti-foaming agent and some other additives using that. I don't really want to go in details on this because I don't think that the recipe itself is very important in this case, but the most important will be the results that I will show you in here. We have cement cores and we have shear bone samples that has been used. For the shear bone samples, we use metal, pipes, tiny pipes, short pipes, as you can see here, with the provided length of 4.45 centimeter, the diameter 1.88 for the inside and 267 outside. And in these ones, they were clean. We pour cement in it, and then we put them in autoclave, and then we expose them to the CO2 environment. Especially for this cement, for the bonding samples, we also use as reference small samples, from which they were originally rectangular samples, and then we cored them and we got cylindrical samples that has been used for testing. And I will show you some of the testing results on that one. Although it's probably not the best way to do aging of CO2, we actually wrote a paper, a very intensive paper, in comparing different methods of aging cement in different cells and so on. This is the most common that you'll find it available. So we use an autoclave, and you can notice here the autoclave where there was the gas phase on top, the water below, and actually we were, pumping the gas on top, and because of the pressure ratio in the autoclave, the gas will start dissolving in the water. And then we are using a heating system where the water was circulated inside. And by circulating the water, we were also accelerating a little bit the solution of gas into the water. We could do here, and we use also methane as another gas to control the concentration of CO2 for this. So basically, we have not used air at all in the system for these experiments. Now, this is a text matrix, probably look a little bit complicated. It's just to show our students are working 24 hours a day, and if they don't finish the test, they will spend also the night to finish those tests on that. But we've done very intensive experiments. A lot of experiments has been also discarded because the results were not pretty good at the beginning, especially for the pre-testing and analyzing the system. The shear bonding strength was done by using a setup like this, which was specifically designed for the small samples. We are using the push-out method, as I presented earlier. And as you can see here, the cement was poured inside of the pipe. And I insist, one of the reasons for that is that we have a very controlled contact surface between cement and the pipe, and that's the reason we prefer this method very much compared to other methods that has been used in the past. And by increasing the axial force or the push-out force on here with a very controlled speed, we've been able then to basically record the data. And as you can see here, the data for this test was recorded up to a maximum value, and then whenever the sample was failing in terms of bonding strength, we kind of stopped the test. That's why, as you remember on my previous paper, we continue to do this debonding until the entire cement sample was pushed completely out of the steel, and just to learn a little bit more out of the experiment. With this in mind, we have noticed some very interesting facts in here for these samples. And keep in mind, there were 14 days in autoclave. You'll notice here that the shear bonding strength is pretty high compared to 1 day typically, which is in the range of 1 megapascal to 2 megapascal. So we used, and you notice here, we have temperature of 107 degrees Celsius, 177 degrees Celsius. And, for those who are really geothermal enthusiasts, we have 221 C, as a very high temperature. And by comparing this data, you will notice actually that at a really high temperature and with 100% CO2, basically we are losing a lot of bonding. So the bonding of the cement to the metallic surface is pretty low compared to all other temperatures. I will show you in a separate slide that we have noticed a very interesting dependence of temperature. But if you look here, we have used also different pressures like 21, 42, and 63 megapascal. And for each temperature, we have noticed a very tiny increase of the bonding strength as a function of pressure. But I will show you later that pressure was not necessarily the most important factor affecting this bonding. Also, on the cement, we start looking at, what happened inside of the cement and how the push out course looks like. As mentioned earlier, at the 177C, we observe, the maximum shear bonding strength, which was very interesting for that. Don't forget, we have added here, silica flour to enhance, the temperature resistance of the cement. That's why the cement didn't degrade at that temperature. And also, we have seen that basically the carbonation, of the cement component are actually expected to improve the shear bond strength in the system. And that was one of the things that we're going to show you later when we've done some other type of investigations. We measure also the volume expansion after aging, just to look at what happened with the average volume change. And you can see here that this is for 42 megapascal. We have noticed some changes in here. By increasing the radial stress will improve the shear bonding. That's a very interesting element because, and I remember we discussed yesterday already about the cement shrinkage as well as the thermal effect of, expansion of the cement on that. And actually, all the, trends that we observe on the shear bonding strength with respect to temperature are in agreement with other ones that were recorded at 42, 21, and 62 megapascal. This is just a little bit to talk about the solubility of CO2 in pure water, which will kind of define what is the meaning for us as 100% versus 10% of CO2 and how that was working in our system. Obviously, the temperature will have a high effect on that, which means that at elevated temperature, the CO2 solubility will be different than, at, let's say, room temperature or atmospheric conditions. And that has to be considered in what happened in our setup with this system. We measure also the porosity of the samples, and we have noticed some changes in porosity. But this time, if you are looking first on the first one at 10% CO2, you can notice that actually at 107C, we have noticed the lowest porosity change. We have it. Whereas at higher temperature, especially 221C, we observe the highest porosity in the cement compared to the others. And this porosity trend was similar at 40%, but totally reversed at 100% CO2. Probably is because of the fact that porosity reduction confirms the dominance of the carbonization over the leaching process, but bicarbonization increases the porosity to the removal of calcium CO3 crystals forming the pores. We believe that the effects here probably needs a little bit more detailed information on that, but it is a clear effect of the CO2 on the performance of our samples in here. And if we compare on the same graph, the samples, for the porosity as well as the samples for shear bonding strength, you can notice here that we have a porosity trend with the minimum at around 170 degrees Celsius. And actually, we have another trend on the shear bonding strength with the maximum, which will be just around 177 degrees Celsius on that. So they are basically reversal in the tendency for that, this might be again the fact that the calcium carbonate crystals in the pore space are the one responsible for that. In order to look a little bit more on the CO2 or if you want acid penetration in the cement and how this looks, we use the standard solution that the phenolphthalein solution that will be applied to the specimen, and by looking at the color we are trying to make now an idea about how deep and how fast this will penetrate into the system. And actually By looking on this, we kept the orientation of all these samples, what you see in this figure here. And, we look at that we could not really localize the increase in carbonization around the bond interface for our system. So the carbonation basically will happen, pretty uniform in the sample, if you want to take it as such for this. This might have some implication in what is the role of CO2 to the bonding process. Now we look and we try to get a spectrum peaks, for the samples to identify whether we can locate some of the elements in the system. And as you can notice here, we use samples that has been exposed at 21, 42, and 62 megapascal. And we observe that the peaks are pretty much identical, with, however, a reduction of some of the elements at 21 megapascal. You can see we have relatively lower components in here, and the maximum was observed at 62 megapascal, which is something that was actually expected for our testing on that. Furthermore, if we move to the consumption of the CH phase, we notice that this was typically consumed completely at 107 and 170 degrees C due to the enhancements of ionic transport in the system. That's at least what we believe on that. And also in the middle and low temperature aging condition, we noticed that the CCH phase was still preserved on that, which is still debatable to a level of how fast, how deep the CO2 as a carbonic acid will penetrate a sample which will be much bigger than our samples, which obviously we have not done in this system. Furthermore, the cores which were aged at low temperature, like 38 degrees C, shows just a partial carbonation of the CH phase, which actually we noticed a little bit more calcium carbonate in the form. So you will notice here that will be our 38 degrees C on the lower end for our system. And this is probably interesting from the chemical point of view of cement, carbonation process as such. Also, in order to identify what happened really in the CCH phase, we try to look at the conditions for the formation of polymorphs. And actually, in most of the cases, we came actually with a conclusion that it is the most prominent form of CCH that exhibits good bonding properties on that. And actually, if we can control some of these changes inside of the cement, we probably will achieve better bonding by this development of the tobermorite gel inside of the system. In order to just validate a little bit what is important for our bonding, what is important for shear bonding, because here we are talking about shear bonding only, we performed an ANOVA analysis, and we look at that, and actually we came out with the fact that the most important is actually the interaction effect followed by the temperature. Whereas the temperature will show either a trend of increasing the bonding or decreasing the bonding, and that's actually the most complex question we have in most of the cements, and that's why we believe that almost every cement we put in a well needs to be first tested for interfacial shear bonding strength in order to make a case whether it will develop better bonding at elevated temperature or low bonding. And if you remember, most of my tests with pure knit cement have shown a decrease of shear bonding at elevated temperature, whereas some of the tests here showed actually a trend of increasing that with the temperature increase. Now, the pressure have shown relatively less effect we believe that what pressure actually will do to the cement is, first of all, will compact the cement and will kind of compensate some of the shrinking of the cement in the system. And then nevertheless, as our fourth parameter, the CO2 concentration seems to have an effect on the bonding with our system. To conclude, we have seen here that two major elements are having a major influence on the bonding, and also we notice that the temperature has a major influence on carbonation of cement due to its impact on the CO2 solubility, ionic transport, and carbonation reaction. Short-term exposure of the cement to a carbonic acid results in carbonation of cement, which is accompanied by a temporary increase of SPS, so shear bonding strength, and reduction in porosity and cement expansion. Nevertheless, CO2 concentration and pressure have some effect on the carbonation process. However, the presence of a strong interaction effect between this parameter and temperature disguises their impact on shear bonding strength. With this in mind, I would like to, thank to the Bureau of Safety and Environmental Enforcement, BSE, who sponsored this project, some time ago, and of course to the University of Oklahoma for providing the necessary project support. And I'm open for any questions that you guys may have.
Okay, questions? We got one here.
Yeah, me again. A comment. In my previous life, when testing, looking for carbonation in cement systems, we noticed that once the carbonic acid hit the cement at the interface, it densified the cement system. So maybe that's helping you improve the shear bonding, because the initial effect of carbonation is to densify the cement and reduce the permeability of it. The issue is once the carbonic acid exhausts and you hit that same specimen with fresh water, that's when you dissolve the system, because calcium bicarbonate is not available, or those phases I've never seen in solid form. They're dissolved in water. So that's how your system begins to reduce, and that's how CO2 can continue dissolving your cement. That's the one comment. So the question I have is regarding your analysis of variance. Typically, when your sample is not very large and you perform an analysis of variance, you actually need to look at a non-parametric test, not a regular ANOVA test, which looks at the variation of a standard deviation, because that is a central tendency statistical model that may not apply when your sample is very small. So what kind of ANOVA did you actually perform? Is it a non-parametric or a central tendency parametric test? No, this is a parametric test. So we didn't perform here a non-parametric test. We are very much aware of the fact that the size of sample will definitively affect the results, especially if we want to upscale them to the real world. But the project, the way we started, was in particularly to be able to do some comparison for that. And that's why we believe that although the size of the sample is small and may not be fully replicated for real situations, at least the test that we have done here, and you can easily follow, for example, in such a graph, shows a very important tendency of the bonding evolution with pressure and temperature. And if you look at the data here, for example, high pressure doesn't really improve the bonding at all, which means that, as the ANOVA was telling us, the same thing, is pressure is the least parameter that will be significant in this process. I fully agree that a non-parametric study will be important,
And, our laboratory right now is trying to expand the testing. We are using sizes. So we are varying sizes now from as low as 1/2 inch to almost 4.5 inches for the cement. And we are trying now to see whether the geometry itself plays a role and whether that geometry change can be at least scientifically explained. Because right now there is only one paper out there that has done some geometrical impact on the shear bonding strength, but the samples were between 10 millimeters to 20 millimeter, and they have shown that actually the shear bonding strength will increase with the geometry change or will decrease with the geometry change. Some of the things, if you remember my paper yesterday, we've seen the same by having our, small scale data. We got around, 4 megapascal. By moving to larger 3-inch pipes, we got something like 1 megapascal. We are still trying to identify what this happened and why happened. But for us here, this is the good news I want to bring is that CO2 may be scary for everybody, but sometimes CO2 may help, bonding, which is, a tiny bit from all the damage the CO2 do in our geothermal wells and so on. But better understanding on this probably will help us to just build better wells and eventually better cement recipes on this.
Okay, here's another question.
So I guess just looking at the trend, do you think it might be a time temperature effect? Maybe if you give the 177 test longer time to degrade, they might get to the same point as the higher temperature?
We don't know that yet. Time was not on our side on this project, but I can give you some good news. My new testing procedure with the relatively larger samples, like 1.25 inch diameter, we do have some samples which are almost 6 months old that we're going to test, and then we hope to be able to get more samples now at different temperatures. So most of my samples are limited to about 85, 90 degrees C because they are atmospheric. But we hope to get some samples that can go to 200 C under pressure in order to do that. So we are still coming there, but it's very tedious time and work. I don't know.
CO2 in just DI water or was it brine? Because that would make difference, I think.
So I don't remember anymore, but I think it was water, so DI water used for the test.
So I have seen some papers not with carbon dioxide, but just neat cement, and as a function of temperature, the shear bond strength increases up to 200 degrees C, and then it starts reducing. So in this study, so I'm kind of trying to struggle that whether it is the CO2 is actually strengthening it, or is it just the temperature which is strengthening it?
So there is only one paper, and probably you are talking about the same paper that has been using this or showing this trend of bonding increasing up to 200 degrees C. This cement is designed for high temperature. So the cement is supposed to be stable up to 250, 300 degrees C. So we don't expect that the cement itself will suffer from the temperature on that. We believe that actually the combination of CO2 and temperature had that effect for the system. However, some of the papers that I've read also with the shear bonding, or particularly on neat cement, I do believe that the test, because they've done the test at elevated temperature rather than cooling down the samples, is that on those tests, they were still having some effects of the thermal expansion of the system that were captured as part of the shear bonding strength and was not the pure bonding strength. It's just my personal opinion on that, but I think that those tests are very important, but the trend is needs some attention on that. Exactly. because I believe that pure cement bonding happens accelerated at elevated temperature, and therefore the bonding doesn't have time to bond anymore. That's the reason why you should see a reduction of bonding at the elevated temperature, at least for neat cement. Whenever you add additives, the whole system behaves completely different. Do we have any questions from the audience? Thank you. Okay, so while I'm preparing here, I would like to then introduce our last presenter for this session. He will talk about two-stage cementing operations in the Salton Sea geothermal field. And hopefully we're going to see not only the problems, but also the solution associated with that. So William Thomas, we're going to introduce this. Will you help him? Start with the solutions.
Yeah. Excellent. Thank you. Appreciate it. Thanks, everyone. So the title of this, well, I'll first go introduction. Billy Thomas. I'm a senior geoscientist at Cal Energy, Berkshire Hathaway company, in the resource and drilling department. The title of my paper is Two-Stage Cementing at the Salton Sea Geothermal Field, but really it's more of an overview of really our field out there, instead of in kind of the cementing operations that we've been doing over the last few years. So I'll go and get into it. So just as a quick overview, the Salton Sea geothermal field is actually not too far from here. For those of, I think most of us in this room have either know it or have even worked in there, a lot of us. It's about 2 hours just east of here, east of San Diego in the Imperial Valley. They're in the southeast corner of California. We operate about 350 megawatts. It's comprised of 50 wells. About half of those are production, the other half injection. And like most geothermal fields, it's a large completion, large diameter completion wells. Most of our wells are completed in 13/3/8. We have one well completed in 16-inch production casing. So, but the majority 13/3/8. And it's been in operation quite a few years. And there you can't see it on the bottom right, but really what I put there is development potential. That's one of the, I think, key factors here with this field is it's currently 350 with Cal Energy, another 50 megawatts at Hudson Ranch, but there's really the development potential there is a lot of papers show over 2,000 megawatts. So there's a lot of players coming in, and with some of the recent CPUC potential for California, I think this field really has a chance to really develop. So I think it's very unique in the its reservoir conditions. So I think solving the cementing challenges, I think there's a good chance here to really spend some efforts in trying to figure out how to best cement a lot of the wells that are hopefully going to be drilled there in the years to come. So quick background for the reservoir conditions. Temperature is 550 to 600 degrees plus. I put 600 degrees plus because there is a well that was drilled over 700 degrees Fahrenheit that got a little scary, close to supercritical, and was just plugged at that time. But wells like that still exist up there, and might be developed in the short term. So the other there, the total dissolved solids, the TDS, is 25%. So extremely saline brine, very, very corrosive. The low fracture gradient, I think like most geothermal fields we work in, fracture gradient's about 0.65 to 0.7 PSI per foot. So it's always a challenge for us anytime we cement any string of casing. H2S and CO2, there is a CO2 zone. That CO2 zone is a little shallower. Just north of where we have most of our wells, there is an old CO2 plant that was operational in the early 20th century. So for the production of dry ice, one of the largest in the US. So good for dry ice, not so good if you're going to be drilling wells in that shallow section. So down to about 1,500 feet for the most part is where that zone is. High permeability, a lot of fractures. So something we also have to contend with in any cementing operation. So the corrosive environment, like I mentioned, you can see just an example here of some carbon steel casing. And recently, I mean, we pulled some carbon steel casing as a hang down liner, just you know, an L80 string. You know, 1 year in production, you know, 1 year in contact with flowing brine can you know, we're lucky to even pull that string really. So you can see there's just for that production casing there's really carbon steel cannot be used. So we use a titanium grade alloy or Inconel 625 for production wells. For injection wells, we can go with the 2507 duplex stainless steel. To give you an idea, I think when we're talking about some of the, you know, in particular the production casing, we measure flow rates in thousands of pounds per hour, but you know, we have one well equivalent that would be equivalent to producing 200,000 barrels per day, right, of brine. So just the amount of flow that goes through them, just the you know, how robust it needs to be essentially to maintain that production for extended periods of time is really crucial. So just a quick overview of our well design here. Actually, we cement a 30-inch surface casing followed by a 24-inch intermediate string. So that 24-inch intermediate string actually goes down and its primary function really is to cross that to isolate that CO2 zone. So that string we run Halliburton's Thermalock cement there, just for added protection from that CO2. But we do see a lot of issues in our casing at that zone across that interface with the CO2. Here's just an example. We drill our next hole section, and we're the two-stage cementing, which I know is a part of it here, but it's really for this is our production casing, 20-inch string. Usually we're cementing that down to about 3,000 feet. We do this in 2 stages. So we use a simple 2-stage DV collar, mechanical DV collar, no ECP. It's very, you know, it's not very fancy. It's really just to ensure we get a good first stage. And we run that DV actually below our outer shoe, or below our out 24-inch shoe. No ECP. Part of the reason is really just to avoid having any channeling, any contamination up in the casing to casing annulus during our first stage. Try and keep that area clean and really focus on getting a good job on our second stage there in that casing to casing. And our alloy string, you know, some of those alloys are, you know, as much as $3,000 a foot. So I think we are extremely cautious anytime we cement any of those, regardless of what practice we use. And in this case, we actually do a full casing to casing cement job. No, you know, no outside risk of any formation of anything. So we make sure we cement that string in pure casing to casing. And then we complete the well, typically 12-inch open hole, 12¼ inch. Now, historically, some of the problems we've had with our cement jobs is it's really poor cement quality. So channeling, also losses of cement. So, you know, a lot of times we're in fractured rock and we simply just can't get enough cement to serve. You know, a lot of times we have losses throughout the job. Some of the channeling I have here that cause a poor casing centralization. So a lot of times we really just minimize our deviation in the wells now. You can see that we do run ultrasonic bond logs for most of our 2-stage jobs and also our alloy or high-end casing jobs. You can see the example on the right there, the kind of the liquid phase. You can really see the channeling we had in this particular cement job. This is a highly deviated well, at least in geothermal standards. Even some areas, I think, with you know, obviously some of the channeling going on here, free water. So, you know, issues we come across, like I say, we run logs on most of our jobs. So we have a good feel. It's some of it's relative. I think sometimes sometimes they all look bad, but we've had logs that don't look great, but we've had a lot of success, and they've been operational for years with no issues. In this case, this is an example of something that was not good. Let's just say. The other problem I have down here, the collapse casing. I think a lot of what we've discussed is kind of long-term, long-term effects of cement bond, all these things. Really, one of the main things that we focus on is placement of cement. And one of the biggest ones, really, if the placement's wrong, or if you have channeling, if you have free water within that casing to casing annulus, you can lose your well the first time you flow it. You can collapse it that first time. So that's something that we take very serious. That's part of the reason why we've been doing this two-stage jobs. So our considerations, really, like I mentioned, low fracture gradient, fracture zones for doing these two-stage jobs. Some of the benefits we've had, we really have had benefits, especially in that second stage. We have very minimal losses, even though we are in somewhat in open formation. We've had minimal losses during that second stage, and ideally, it's just to minimize the potential for that casing to casing. The casing to casing annulus, to make sure we get a good cement job in that section. Here I do have allowed the use of 2 different cement slurries. For the most part, we try and cement with as low a density as we can that still has good compressive strength, but we're looking at anywhere from, I think, like most typical jobs, anywhere from 13.5 to 15.5 pounds is what we use. Here's another example here. So some of the benefits, really, we have had improved cement bonding, improved return cement to surface especially for the second stage. Here's an example another example on the right, where we did have a much more successful job. So we've had some success, some not so successful jobs. I think for future considerations, we've talked a little bit about, foam cementing. I wasn't around there, but we have wells that have been cemented with foam that were successful in previous years. I think operationally, it's just, it can be a little bit cumbersome sometimes. I think we've gone away from that recently. We've also done liner tieback successfully. The last well, I think 2009. Was a successful liner tieback job. The last 2 I have down here, the reverse circulation, is something that we haven't tried. We've been looking into doing some reverse circ jobs. But again, that really comes down to operational expertise. Some of the, we've had discussions about doing these, but I think one of them is really having the confidence of the people actually pumping the job. I'd say, when it comes to actual operational, we don't just worry about the operation itself, but it's so time dependent just from a temperature standpoint. If there's some downtime during pumping, what have you, and the well starts to heat up, you could lose the well on that specific job. So really having the expertise. I know we've talked a little bit about reverse circ jobs, but I still don't think they're just as common, especially not in geothermal. Most of what I'm familiar with still is either a single stage or a liner tieback. It's pretty common. I know, Indonesia, other places are really focusing on that type. So on that type of placement. The other lightweight cement, I've looked into that a little bit, but really very little success in there. We haven't really ventured into that area, and that's really all I have. So. Just an overview of the field is really what the idea here was to present, and also moving forward, hopefully there are a lot more wells drilled in that area. So yeah, thank you guys.
Okay, so Daniel's got a question.
Yeah, good talk. Thanks for the presentation. Just curious, what types of mud systems are you using? And have there been any variation in that? Do you see any pluses or minuses, or is it all pretty much some type of gel system?
Yeah, just a gel system. We run, I mean, we drill these with so many, you know, a lot of times we are drilling with losses, but we run a polymer system, also polymer mud. The channeling that we had there was, you know, it was a little challenging on that channeling job. Just, I'm not sure if it was something from the mud or scavenger. We had there was a lot of things that, a lot of factors that went into that example I gave there. One of them being mud centralization. So there was a kind of a combination, I'd say. It wasn't just one thing.
Right.
So it's hard to pinpoint, but
sure. Is that's not bentonite? Are you talking attapulgite or sepiolite for your gel drilling fluid, or you're not sure?
no, not sure. It's mostly polymer. I mean, it's not, you know, we're running a polymer, so it's not a bentonite system.
Okay, thank you.
Here we go, Bill.
There's a touch of bentonite in it. It's, I can't remember the name of the polymer right offhand, but they do use a little bentonite, but it's very little. Xanthan gum, thank you, xanthan gum.
Is it on now? Okay. I said xanthan gum degrades at pretty low temperatures. I'm thinking carbonized, but I mean, I just without carbonation at all, it dies. It degrades. The polymer degrades at one. Well, xanthan is lower. You're thinking Welland. Welland goes to like 275, and then diutan might go up to 300, a little more. But xanthan's around in the 150s. Just FYI.
Okay, how are we doing? Yeah, anybody else right here? We'll take a question or comment online. So here's one. It says, let's see, only the bottom one. Okay. Simon asks, have you looked at using glass microbubbles in the cement to manage the trapped annular pressure? Shell has done some work in this area for steam injection wells, SP 184102.
Yeah, no, we haven't, but ideas like that are really what we're eager to look into. So, but we haven't, no.
Okay, haven't yet. And there was a discussion on microbubbles before, I believe, on a previous presentation. Who else? Here we go in the back.
So thank you very much for the presentation. I know as far as the reverse cementing is concerned, Resource Cementing has done numerous one of those, whether it's on casing or in the wellbore. And we'd like to have the discussion with you.
Yeah. Excellent.
How to improve that. So
Thank you.
Okay, another one.
Thank you very much for the presentation. I was just a recommendation. I've seen situations like this in the past, and there are other alternative solutions. Probably simpler, expensive is using a specialty spacer that you can use to seal the formation. So then the density of the cement slurry is not going to be a problem. and you can reach surface. So
Yeah, thank you. Yeah, we've tried in some cases, we have, minimal losses where I think we've even used, we'll run LCM within the slurry a lot of times. There's just other times where really we're dealing with fractures where, the returns, it's just not going to happen. I mean, we have some injection wells, for example, that, take 8,000 GPM on a vacuum. It's some of the fractures down there are just, it's a different ball game. So that's not always the case for cementing, but when we have minimal losses like that, I think, we look at some of those ideas. But thank you.
Okay. Sam?
I think what Billy made a comment about 8,000 gallons per minute of losses. Come over to Hawaii, I'll show you, you can walk through a lava tube,
Yeah.
which is probably more than that. But at the same time, we have achieved returns to surface. The first time, one is with reverse cementing jobs. And the second thing is what he just pointed out, using a spacer. That's very special, but does take care of that. And this has been proven again, like for example, in Kenya, we cemented a string on the same pad. They had got 16 top jobs to be done, and we did it in one. So just think of that. There are options available.
Excellent.
But certainly
Excellent.
it takes a little bit of looking into the system, looking at what are the benefits, but certainly there are benefits available. And
Excellent.
proven technology. There's nothing that we are thinking of going to Mars or going to Mercury. This has been proven and can be applied.
Excellent. Thanks, Sam.
Okay, this is great. Great conversation, and it's me again, right?
Oh.
So reverse cementing, well, the one comment on the mud system, I wonder if you looked into biopolymers, those that hydrate pretty quickly regardless of the pH. Those seem to do the trick in those environments. And secondly, reverse cementing is quite prevalent in geothermal. I mean, at least 27 jobs that I've been on in the last 20 years have been geothermal. And the other thing is, the one comment I want to make is, not too long ago, stage tools were a no-no in geothermal. We were all afraid of leaving a pocket of water right at the ports where you start the second phase, the second stage. And maybe Brennan and Bohr here can comment about their experience in Hawaii. That can cook off and shoot casing out of the hole. So how are you mitigating, how are you preventing from free water or naturally occurring brines to basically remain in around the area where the ports are for the stage tool?
Right. That's part of the reason. So that's part of the reason we actually put that DV collar down below the intermediate string of casing, because there is a little bit of uncertainty there as far as what that interface is between the first and second stage. There's just some risk if you have that hard cement in that first stage and that second, if you do have some water in there or what have you, some free water that's built in, that's come up into that, in that little pocket. So we run the DV collar below, below the 24, in our case, in this case, the 24-inch shoe. And with the risk of, if there is something there in that interface that doesn't look very good, we so be it. We know we got that second stage where we feel comfortable with that casing to casing, and we're okay with that interface is down 100 foot below the other shoe. Exactly. It's probably not cement there anyway after that first stage, so it's hard to tell. I mean, we've run the on our bond logs. Sometimes it looks a little, doesn't look quite as good, but we've had success there too. So, but yeah, at the end of the day, really, it does come down to we'll live with not having a great cement job formation to casing just to ensure we have that casing to casing solid.
Okay, great to hear from somebody actually operating, doing the work as well. Who else? Any other questions? Okay, well, thank you very much. Do appreciate it.
Thank you, guys.
Thank you. Not sure how many problems we solved or how many solutions we got, but at least we have at least 5 more minutes for the coffee break. So enjoy more coffee.